Yes. Guys, take out your notebook and we will do some notes for today. You can also take out your Chromebook and do the notes there as well.
Of course. I love doing notes.
I mean, it is easier.
Definitely easier. Notes. Is that my water bottle? Short-term memory. It's your quest.
All right, class. You're gonna title this atomic structure or quantum. Just title it quantum mechanics. Right. This is just a brief introduction, but mostly we're just going to analyze the history of the atom.
The history of that. It starts at the beginning.
Yes. So now here we have wave phenomena. So Newton found out that light had some particle composition, just like the light we see, particles. Huygens, on the other side, he said that the light was in modes of waves and not particles. It was not later until Max Planck in 1905, through black body radiation, that he discovered that that light was both particle and a wave. But we also have Maxwell, and Maxwell developed a set of equations or established electrodynamics in which it treats light both as a particle and a wave. I'll tell you what to write. So, we also experienced in 1905, Albert Einstein won the Nobel Prize in Physics, not for his theory of relativity, but rather for his explanation of the photoelectric effect. And basically, the photoelectric effect was, let's pretend this is metal, and he would shoot, or he would turn on a light bulb. You can think of it as light. The light will shine on the metal, and based on the frequency of the light, so if we increase the energy of the light, then there will be some electrons being expelled. So for example, for this light, let's say that it's shining on the metal, there will be no electron ejection. Why? Because there's not enough energy in the light. How do we increase the light? Well, we increase the frequency, or we increase the energy. By energy, I mean that we can increase the energy, such as X-ray or gamma rays, and this will expel some electrons. And how would we notice that the electrons are being expelled? Well, we can notice it if we put like a sensor or something, and it will conduct electricity. But that's another story. But Einstein won his Nobel Prize through that. Oh, here it is, better. You can write these two bullet points. That's important in the history of quantum mechanics. So again, Max Planck proposed the quantum theory. And why did he propose this? Well, it's because, again, during that time there was a problem called the black body radiation, which you don't need to know, but just know that he solved it. And when he solved this, he said that energy came in discrete values. By discrete values, we mean that it come out in values that repeat themselves. So, for example, numbers we have 1, 2, 3, but we can now have 1.5 per se. And through that, he also discovered some values like Planck's constant, which we will go over in a second. But again, we have Einstein, that explain the photoelectric effect. And with that, with the discovery, so what did he discover with the photoelectric effect? Well, he discovered that you can only have electron ejection not by the intensity of the light, but rather by the energy or frequency of the light. So these two are again very important. Copy only this bullet. This is very important. Each packet of energy is called a quantum of energy. So why is that important? Well, because so we have light here, right? Let's pretend it is light. Some particles of light. Let's pretend this is light. The light, let's say this is a light bulb, right? I don't know how to say that's a light bulb. And there's light being ejected. So how is this both a particle and a wave? So light is both a particle and a wave. And this particle is called a photon. So what exactly is a photon? Well, again, we say that a photon is both a particle and a wave. So how do we draw that? Well, we have something like this. A packet of energy. And this packet, there's a wave. When we have a concentrated wave, then we have this photon or particle. Photon. So again, what is a photon? It is a wave packet. Isn't that interesting? Very interesting. The photon is also sometimes called quantum. So quantum slash photon. Put quantum. I think in high school they call it quantum. I don't know why. But in the science community we call it photon. Let's continue. So now, here we have the equation for energy. This equation for energy was again discovered by Planck. And we have energy is equal to Planck's constant times frequency. And this frequency, F is equal 1 over T, where T is period. You don't have to remember this, but just know that this is the formula, which is shown here in yellow. So write this first bullet, write the first bullet, and write this equation here. Again, write this first bullet and the equation. So energy is directly proportional to frequency. Whenever frequency increases, then energy increases. If energy increases, then frequency increases. What does this mean? This means that H is constant. H is the same value no matter what. So H is the same value. So again, H is the same value. F increases, then E must increase. If E decreases, then F must decrease. So just write the first bullet. Here we have so-called the blue shift and the red shift, in which we're not going to talk about today. But by blue and red shift, um, a very good example that it does not involve light, but rather sound. Still recording? So let's say that you're here, right? And let's say that there's a police car here. And the sound radiates like this. When the police car is approaching you, then the way that you're going to perceive the sound will be like this. Meaning that the distance from here to here increases, while the distance between here decreases. And therefore, it will be called blue, or the frequency will be higher. So once the police car passes by, then these distances, the radii distance between the sound decreases, and there will be a red shift, or lower frequency. So now copy this, this, and this. So don't copy the last two. The last two deal with electron volts, but we won't talk about electron volts. We only talk about volts in this class. Just know that energy is equal to Planck's constant, which is 6.626 times 10 to the negative 34 joules a second. And frequency, again, is 1 over t, the period, or s to the power of negative 1. And the SI unit for frequency is also known as hertz, which he first identified the photoelectric effect. All of this is modern physics. So all of this is actually currently applied a lot, whether anything has to do with light or frequency. So the higher the energy, that means the higher the frequency. So the frequency, for example, we have radio waves, and then we can have some sort of UV. However, when we increase the frequency, so we go from microwaves to X-ray to gamma rays, then this light has more energy. It has so much energy that we cannot see it really. So for example, if we go to take a X-ray, there's a slim chance that the light of the X-ray might damage your DNA. Why? Because the X-ray has large amounts of energy that can basically break apart or deform your DNA, damage your DNA. Why is there this chance? Well, because of the energy. The frequency increases for X-ray, then the energy increases, and it's damaging you without even noticing. I think the most prestigious lab in the US to work as a physicist is Los Alamos lab, where the nuclear bomb was created. However, it is said that if you just stay there working, you gain, I think, times 3 X-ray than a normal human being. I think for 3 months or something like that. So working there increases your chances dramatically of developing a cancer. So imagine being a scientist working in the most prestigious lab in the US, and then you develop cancer, right?
Educational.
However, light could also be treated to treat other forms of cancer, like any type of cancer, really, which I might do in the future. So let's continue. So now here again we have a photon. Copy this. A photon has 0 mass. A photon is also known as a quantum. And that's about it for that. So just know that a photon, or light experiences zero mass, even though it's both a particle and a wave. So now here we have the particle collisions. Your turn off?
No, I was wondering if it's still recording.
Okay, thank you. Now here we have particle collisions. So again, in the photoelectric effect, we have this light that hits. And how do we determine the energy? Well, we can also correlate the energy or the kinetic energy of that particular moving particle. So what is kinetic energy? It's energy that moves. And so this energy, or the equation, so copy this. This will be momentum equals Planck's constant times frequency over the speed of light. So what is the speed of light? Well, the speed of light has a value of 3 times 10 to the power of 8 meters per second. So what do you have to copy here? You have to copy the first bullet and this equation. This equation is then equivalent to Planck's over wavelength. This is a very beautiful equation indeed.
Are you okay? Are you falling in love with the equation?
Oh no, because it's very simple. Usually, equations tend to be very long in physics. In high school, we only see the smallest ones, or the simplest. But it takes incredibly amount of work to make an equation very simplistic. How do you say it?
Simple?
Simplistic. Like E equals mc squared. Like behind that, there's a bunch of work, a bunch of really difficult mathematics.
Thanks, Einstein.
Good job, Einstein.
Isn't it crazy though that you can identify the energy of something just by multiplying the mass times the speed of light?
Not if you don't care.
That is true.
What if you don't know the speed of light?
Sorry?
Talking with
Are you don't know what the speed of light is?
I do not know.
Tell him. Tell her what the speed
I
of
need
light
to know what the
is.
speed of light is.
Well, the speed of light is just how fast light particles travel per second.
Yeah, what is it?
Does that have like
3 times 10 to the power of 8 meters per second, which is really fast, right?
Very fast.
So,
Good example, it takes 8 minutes for the light of the sun to reach
Did you do it,
Earth.
Chastity? Hold on.
I did say it.
What did you say?
It takes 8 minutes from the light of the sun to reach the Earth.
Nice.
Nice for you.
it is what, Chad?
It takes 8 minutes for the light of the sun to reach the Earth.
Right, so the sun exploded, we wouldn't be able to do anything. Right?
Yeah.
We will notice it 8 minutes later when we're on there.
I
So
did-
no. So like for example, this is actually interesting. So
Being
like
loud if you-
so let's say that the sun exploded right now, right? Which is it is possible.
That's bad. Hopefully
Let's say it explodes, right?
Uh-huh.
Then we will when we see it, it already happened
8 minutes ago.
8 minutes ago.
Wow. We've been doing for 8
So,
minutes.
so you take the same practice or the same principle for other stars, right? So you're basically looking back in time just by looking at stars that
Well,
are.
time is relative.
Thank you.
Sorry?
Time is relative.
Let me finish.
Time is relative. So is space.
It is relative.
But it's still a unit of measurement.
The theory of relativity.
What are you talking about?
The theory of relativity.
I know you're talking about.
Okay.
Anyway.
Time is relative, but yes, there's a lot more complicated math going into that. There's some Riemann geometry, which is really complicated math. There's a special and a general relativity. General being the hardest.
I'm sure the recording. Like,
Okay, so you're gonna copy the first one, the second one.
The third one.
And the last one. But basically, here we have. Lisa, do you know this model?
Yeah, sure. Yeah, what is it?
Boars.
Oh.
Bohr's model, correct.
Wow, she's so
I know.
smart.
I had my physics class 2 periods ago, so I have a learning curve right now.
We
Okay.
learned that in like biology. Or chemistry.
I wasn't good at either of those.
Ooh. What
But
is
isn't
it?
this crazy?
Isn't
Like,
that
how do
like
you
the
come up with this model, right?
Bowls?
Well, they
No,
start.
there's like a, is there like a bowl model where like it's like the dots on like, and like,
Isn't that the cloud? No.
Right, the most modern method of electron.
what is it?
So here we have the atom, right, or the nucleus with a proton and
I know
neutron.
that.
That's it. That's
But the cloud model would be like that.
Electrons. But the thing is like, what is it called?
the cloud.
What is it called? It's called Schrodinger's model.
What?
Schrodinger's
Like,
it called?
like the cat?
I remember
Like
you
the
yes,
learning about it.
quantum
Like
model.
the cat in the box?
Cat in the box.
Right, cat in the box.
There's
So
a board.
what does it mean to be class? What does it mean to be the cloud? The bunch of dots is basically
Electrons?
Valence electrons?
no, it is electrons, but it's the probability wave distribution of electrons.
Of course, yeah. We all knew that.
Now we do.
Wait, but also, no, I was wondering what this model is called. Give me a second.
You mean the cake model?
The cake?
model.
The
It's
It's very
like,
outdated.
Shakes it.
it's like,
It's very outdated.
what's that called?
Oh, that's in chemistry. I don't know.
Yeah. Oh. Well, well,
Well, they do this model just so that
Protons.
it's easier to
to see the valence electrons.
right
Yes,
the
yes.
shared electrons.
Of course.
Um,
I didn't fail my AP biology test or nothing.
It's also.
but the real or the most
Shady.
or the most accurate model to date will be the cloud model, and we will. I think there's a picture in this
Schrodinger?
Schrodinger's model.
Schrodinger's.
Schrodinger.
Schrodinger.
I say it in German, or whatever it is.
Well, you do say it's Schrodinger.
Schrodinger.
Oh, that's very nice.
Like Einstein, that's English, right? In German, it's Einstein.
Is
I like
he
that, you just-
Polish?
Einstein.
He lived in, or he's Polish, but he lived in like Germany.
Ooh, it's sexy.
Anyway.
Sorry, that's just funny.
All right, I'll wait 1 more minute, and then we can continue.
Can I have a, what?
Huh?
No, I asked in the C-bar, I was like, when I give him an egg, he said, she's a yes. I was like, okay, so I will have one.
But isn't it crazy that an electron is both a particle and a wave?
Yes.
It's basically, what is an electron? Basically this.
Wasn't it just, it's a particle, but it has like wave behavior?
Right. It's
Grows
matter.
a giant beard.
It's matter, but since it's so small, it also acts like a wave.
Wait, isn't it only a wave if we like,
When it passes through things?
no, like if we
It goes in
Notice
It
a,
goes
it, you
through
know?
the medium.
isn't it like a zigzag? No, it has like a specific pattern that it goes. It has like a wave pattern, but like the behavior of a wave.
Yeah, it's like that. Like Lisa is doing it. It's basically like this.
I don't remember. A slant? I don't know.
It's
Listen,
called
I just follow this-
parabola.
No.
No, it's very unpredictable. It's just like moving like that.
I got all this information
A
like an
double
hour and a half
helix.
ago. Okay.
Really? From Miss Boyd?
Yes. Except for we didn't go through the slideshow. We just like watched the videos and said, okay.
So now we have the Bohr model, which you all are very familiar with.
Oh, the configuration table. I forgot I hated
Oh, I hated
There was a time during the Soviet conference in 1927
Thank you.
that they were fighting for the
For
the-
glory, yeah,
for glory, yes, for the idea of the atom. It was
Yeah.
Bohr and Einstein against Schrodinger
No.
and some other scientists. In the end, of course, Schrodinger won, but they adapted the Bohr model because
Oh.
Bohr was famous at the time.
You got some text messages?
Dude, I never learned that.
Oh, wow, she's talking about social media.
So we're just talking about excitation. But
Oh, look at the
here we have the cloud model.
Yay.
So again, the electrons are not confined in specific orbits.
Uh-huh.
Just like the Bohr model says that it is confined in one orbit,
Uh-huh.
they kind of adapt the classical physics, right? Which is like the idea was kind of like planets, right? In which you have like some rings.
Mhm.
But it does not say here. But Schrodinger adapted this, and you can see that the electron. I don't know if you can get to see, but it's bouncing around. And all of those then dots are basically the probability of finding the electron. So for certain elements, you have the probability is different. Yes.
So, how do like electrons move? Like, not like I know that like they kind of like teleport or something like that. Like do they like move towards it or like do they kind of like teleport?
Teleport. That's interesting.
Teleport.
Come on, tell us, Mr. Physicist, huh?
I mean, it's
You
hard
are
to
you bachelor's.
it's hard to say because
You have your master's or the bachelor's?
my bachelor's in science.
I don't think he's doing enough on that.
I guess so. You could have took.
It's very difficult to say because yes, they do travel like around,
Uh-huh.
but there's a certain probability that it could probably teleport. I would say.
Uh-huh. But the thing is that well, you can't see it, but they do move like in a straight line, so they don't just appear. So they just.
They don't move in a
No.
straight line though.
Well, the thing is like, well then,
Yeah, no, they kind of have like a little.
but the thing is that like,
they have a pattern.
yeah, they have a pattern, but the thing is that like, from one spot to the next spot, they have to like move in a straight line, or else like, like.
I mean, kind of.
Yeah, there's more equation to that,
Do all of them right now.
but
We're going to be the next Einstein. Let's go.
it's difficult. I cannot answer that
What
question
are
right now.
quarks?
I can show you.
Are you gonna answer me?
What is it?
What is a quark?
Sorry?
What's like a quark?
A
A
quark?
quark is something smaller than an atom.
Oh.
We'll talk about that later. For right now,
We're never gonna talk about it ever again.
I think that's enough.
Okay, I guess it is. You want to stop recording?
Oh no. I have some papers to pass around.
So you have to get that and then.
He will record us doing the
Pass,
papers.
write it down. Thank you. This is just definitions for this week,
Oh, nice.
but it will count as your completion grade for today.
Actually.
Alright, I got you.
Like, actually? Did we turn it in? Did we turn it in?
Yes.
I'm not pretty sure again.
From who?
Oh, well, the science club sure turned in, and apparently they gave a free one with the rest of them. So I wanted it, and then she said, why would you want it? It's a 3X. I'm like, alright.
I'm never gonna leggings. Give it over here.
No, I'm gonna wear it. That's one of my signatures. I'm just like- It says,
Can't wait to slowly
it says barefoot. Barefoot.
Is that the science book? Science book. Science book?
You can work
Yeah,
this and see.
we're barefoot.
It does not matter.
Bare in the
Oh, thank you.
Oh yeah, congrats.
Am I gonna get a grade on this?
Yes.
Okay.
Negatively
charged particle.
It's very difficult. Lisa, your question back again. Let me show you what I mean. Let me see.
Oh, what are you gonna do?
Do what?
The
I don't have a pencil. No, I
Yeah.
don't.
I just took.
Seventh period is.
Can I nullify this?
Why?
Because I took my AP English test today, and everybody
Well,
else
still
went
for a
home.
grade, right?
Huh?
Still for a grade.